So here's my fly, and this will be the male, and it's going to have sort of normal body, wild type, right? Here's going to be my female. I apologize. It's going to be horrible, but it's going to have an ebony body, and my artwork is horrible, and sepia eyes, which isn't blue, but I don't have like a light brown purplish, so there we go. Okay, so you get the idea. We're going to cross these flies, and I know for a fact that sepia eyes and ebony body color on the same chromosome, but let's just pretend you don't know that. So for the parental, we're going to go Mendelian, and we're going to cross a pure wild type eyes, wild type body. So this is wild. And we're going to cross that with the recessive sepia. It is recessive, sepia eyes with the recessive body type. Okay. And then, of course, you know, F1 is going to result in all heterozygous individuals. They're all going to appear wild, but we know because we're conducting the experiment that they have they're carriers for the recessive sepia and ebony body. So then when you go ahead and you cross two of these guys to get the F2, you would do that whole assume independent assortment. And you would cross those and assume then that you would get the 9:3 to 3:1 in phenotype. So 9/16 of your offspring should look wild. 3/16 should look wild eye ebony body. 3/16 should be sepia eye wild body, and then the 1/16 you might expect to be the recessive sepia and ebony. Okay, but when you run your chi-square, it turns out what you expect and what your outcome is really different. And so you run the chi-square, and you have to reject the null hypothesis, because it's just statistically, your outcome of observed offspring is just statistically super different than the 9:3 to 3:1 you expect. So you should probably start and say, well, is there a huge difference between male and females? Because maybe it's sex linked, and you find out, no, there's really not. It's just, you know, my numbers are off. So it's probably more like a 3:1, where you have like 3/4 wild and 1/4 recessive, and maybe some freaky weird ones that you weren't expecting in really low numbers. So here's what happens. So this is probably due to linked genes. So linked genes versus independent assortment. So I'm going to start with a heterozygous for independent assortment. Literally means that all the alleles are on separate chromosomes, right? And that's how they're able to independently assort in meiosis. And so that's where, you know, big E could end up with big B, or big E could end up with little b, or little. That's where you get the 4 different possible for gametes at the end of meiosis. But if they are linked, which most things are, that means that they're carried on the same chromosome. So big E is on the same chromosome as big B, and little e is on the same chromosome as little b. So the only way for this parent to exist is to have this, right? That's it. All right, well, this is a nice, simple little Punnett square. So this is independent assortment. And then this is linked. Okay, so if I'm going to cross 2 F1 generations that are heterozygous and they're linked, then I'm going to get parent 1, whose gamete will have this chromosome at the end of meiosis, or this chromosome at the end of meiosis. That's it. That's my only choices. And then again, the same here, which means I am not going to get that 9:3 to 3:1. I am going to, however, get a 3:1 of wild type versus the recessive looking parental type. I hope I did that right. I'm going kind of fast. And then again, you can run the chi-square and say, hey, yeah, this matches more like my observed. And then any of the ones that you don't expect, those are recombinants, and that means crossing over occurred, right? So that means if you get something other than the parental looking types, that means these guys switched place and crossing over, which gave you a few weird ones. Genetic variation doesn't hurt.